everyone. Today we are going to start a new chapter which is on potentiometer and potential divider. Okay. So this we might have studied in school a bit. So let us recapitulate. Potentiometer is basically a long wire. So it's a long wire with uniform cross section, and then if we want to measure a unknown voltage source, DC source, so what we can do, we can say apply first a voltage across this wire, and we have to connect this unknown source like this. So this is a known source. So known source called the EMF equal to E. This is an unknown source. We want to measure its EMF. So we can take a galvanometer or an ammeter. We will connect it like this, and this point is a key, is a jockey. This can move along the length of this wire. So you can move it from here to here, or you can move it to another point. So likewise, so you can move this point. Okay, so you have to touch this jockey somewhere on this wire, and you have to adjust this position of this jockey until and unless you see zero current or zero deflection in this galvanometer. So this is the simplest, conceptually simplest notion or idea of a potentiometer. Okay, and then how do we measure this unknown source? So if this is Ex, okay, and if this total length of this wire is L, okay, this is the total length of the wire with uniform cross section. So this is with uniform cross section, and say we are adjusting the position of this jockey. Now we know that the total voltage from here to here is equal to E. If this is not connected, then definitely the total potential from here to here between the two ends of this long wire is equal to E. So if I take this point as my reference, that means 0 volt, then this side is at E volt or at the potential of E, and then this potential gradually increases from left to right, gradually and linearly increases. Okay, so you can estimate the current through this wire, which will be equal to E by I equal to E by R, where R is the total resistance of this wire. Wire means this wire, not this connecting wires. Okay, so this is a bit of recapitulation. You might have studied this thing before. And say this R is resistance per unit length okay, then that means R is actually R by L, and therefore if we consider a point from So at a distance of small l from the left up to this, okay. So if we consider a point here which is at a distance of small l from the left side, then the resistance here is, so this resistance, call it R1, then R1 will be equal to resistance per unit length R multiplied by small l. So this is RL by L. Okay, so this is R1, and then the potential drop from here to here, okay, call this potential drop as E1. Okay, then E1 we can write this as this current I multiplied by this resistance I multiplied by R1. So this will come out to be, now I is equal to E by R, and R1 is this, can cancel this. So we have E L by L. So you see that this potential at a distance L from the left, so we are calling this E1, so we can call this E1 L because it depends on L. Okay, this is a linear function of L, it increases from left to right. Now if we get a null deflection when this jockey is at a length L, okay, so if we have null here, if we have null deflection when the jockey, that means this arrowhead, when the jockey is at distance L, that means the potential difference or the voltage of this unknown source is same as the voltage here. So these two voltages are same, that's why no current is flowing in this circuit or through the galvanometer. So we can write then that Ex is equal to this potential E1 L, which is same as E L by capital L. Okay, so therefore we can measure this unknown Ex using this equation. Okay, so this is the principle of potentiometer, and now some small points that you must note. So note 1, okay, is that if I have plus on the right side and minus on the left side of this battery, then the unknown source must also must be also connected in the same way, plus on the right side, minus on the left side. If you connect it in the opposite way, then you can never get a balance. Okay, because if so this side is minus, this side is plus, so this is my reference point. So from here to here potential increases. If I by mistake connect it like this, plus and minus, then this is at 0, then with respect to this point this is at a negative potential, and with respect to this point this is at a positive potential. So this is at negative potential, this is at positive potential, so there will be a current, always will be a current, so you can never get a balance. Okay, so this is very important that you connect the polarity of these batteries properly, correctly. Okay, they should have the positive side in the same direction and the negative side in the same direction. Okay, so the batteries or the cells or the sources must be connected with proper polarity. Okay, so by this I mean what I already have said. Okay, so if you are taking minus on the left side here, here also the minus should come on the left side. Okay, similar. Okay, then another note, important point is that, so we can measure Ex only if this E is is higher than this Ex. Okay, so we can get a null point only if Ex is less than E. Okay, so I mean, because if E is smaller, okay, that means say if E is 2 volt and this is say 5 volt, if that is the case, then from here I have 0 volt, this is at 2 volt, and now if I move this jockey from left to right, so then I am traveling through a potential of 0 up to 2 volt. Okay, so I will never reach the potential of 5 volt, which is the value of this Ex. So this potential will never be equal to the potential at any point on this wire. So we can never get a balance. Okay, so this is also a point. Now the diagram that I have drawn is only for our understanding. This is not the practical way to use a potentiometer. Okay, so this scheme is only for our understanding. So the above scheme is not practical, is not completely practical. Why? Because see, we are assuming that this potential E is present across the length of this wire. Okay, so we are ignoring any drop in these wires which may be there. Okay, so we are firstly ignoring the voltage drop in the connecting wires, connecting wires and leads, etc. Okay, so there will be some drop here, there will be some drop here, depending on the amount of current that flows. So there will be some drop. So this will not be E, this will be actually less than E. Okay, so this is one problem. Then next, so practically all batteries, all cells also have some internal resistance. Okay, so there will be also some drop in the internal resistance. Okay, so that therefore also the voltage here will be less than E. As some current flows, there will be some drop in the internal resistance, and therefore we will have a voltage here which is less than E. Okay, so we also ignored the internal impedance or resistance of the source. Source E. Okay, then also normally, I mean, even if we ignore these 2 points, there is another factor. The factor is that all cells, all practical cells, they discharge slowly as we draw more and more current, and therefore their EMF slightly decreases with time. Okay, it decreases more or less with time. It's not a constant EMF. So as we are drawing current constantly through this battery, so the EMF E will also decrease. Okay, so all batteries discharges with time. So EMF of the source E may also decrease with, may also drop with time. And finally, another thing that we require is that, so if we want a precise measurement of this unknown EMF, then definitely we need to know the EMF of this cell very precisely. Okay, so we need a cell or a battery for which the EMF is known very precisely as possible. So we also need to know the EMF of the source E as accurately as possible, as precisely as possible. So we need a source for which the EMF does not change much with time as it discharges. It does not depend on any other factor, maybe environmental factor, temperature, etc. I mean, it should not depend on any other factor, okay, or it should depend as minimally as possible. So we need such a good source, such a reliable source. So therefore, we need a source whose EMF is known very precisely and which does not change much due to discharge, due to any other factor, environmental factor. It should not change much. Okay, so such cells are called, such sources are called standard source. And in laboratory we use a standard source which is which could be made up of some mercurous sulfate based thing. I do not remember the exact chemical composition of the source very well. You may study this from the book or any other source. This is not that interesting. You may just study what is the chemical composition, but from the perspective of electrical engineering, the chemistry of the source is not that important. We are not going to talk about that here. If you are interested, you can read it from the book. Okay, and so the important fact for us is to understand that this is a source of EMF for which the value of EMF doesn't change with any other factor, temperature, whatever you can think of, and its value is known very precisely. Okay, so a standard source, such a standard source often has a EMF of something around 1.083 something. Once again, this value, exact value you can study from volt, exact value you can study from the book. The exact, this you need not memorize. So the point is, this value is quite constant, also in a sense that if we manufacture, if we prepare such cells 10 times, then this value is going to be very close to this value. It is not going to be like 1.09 or 1.07, it is not going to change much. So it is such a reliable source which we can rely on. Okay, so now how to use this standard cell? So we cannot use the standard cell like we have used here. So we cannot put the standard cell here directly. Then what will be the problem? The problem is that definitely standard cell means its EMF is constant, but there will still be some internal resistance, there will still be some wear resistance, and as some current flows, there will be still some voltage drop. So this will not be equal to the EMF of the standard cell. So we cannot use it like this, because if we use it like this, there will be voltage drop due to internal resistance, due to wear resistance, etc. So how do we use it? We use it as follows. So let this be the wear of the potentiometer with uniform cross section, that means uniform resistance per unit length. Then we take a battery, a normal battery, not a standard cell. We can connect it like this. This is minus side, this is plus side. We can take a rheostat, okay, and then here we connect it like this. Now this is a call this E1 or ES. Okay, so this is not a, okay, not S, this is not standard cell, so call this E1. Okay, so this is not the standard cell. Now what we will do, so we will use the standard cell, okay, call this ES, and we will also have an unknown source which we want to measure, call this EX. Okay, we will connect the minus side of all this together on the left side. So this is the potentiometer wear, and all the minus sides are connected to the left side. Now what we will do, we will connect first, say, a galvanometer to the standard cell, and there will be a jockey on the other side. We will move this jockey to a suitable position. Okay, so let me also write the steps how to use it. So the steps, step 1, say if the length of this wire is, say, around 1.1 meter. So this is 1.1 meter, and say if we know that the unknown source has a value of around maybe 2 volt. Okay, so we expect the, so this is the expected value. Expected value around 2 volt. It can be 2.1, it maybe can be 1.8. Okay, but it's not going to be far from 2 volt. Okay, so therefore when we will measure this EX, okay, so okay, before that what we will do, say we will set this jockey, say at a length, say if this is 1.08 volt. Okay, exact value I do not remember. Say for example this is the value 1.08 volt, this is 1.1 meter, or which is same as 110 centimeters. Okay, so we will put, say, this at a length, say 50 into 1.08. Okay, So how much is this? Do you have a calculator? So 1.08 star 50, this is 54. Okay, so 54 centimeter. So what we will do, so we will set the jockey at this length 54 centimeter. Okay, so this is a chosen value, so this is our choice. Okay, so this is 54 centimeter where we have kept this jockey, and then we will adjust this rheostat, call this R1. Okay, then we will adjust R1 until we get a null here. Okay, so when we will get the null, we will get the null if the potential from here to here is 1.08 volt, because this is 1.08 volt. So if we adjust this, then different amount of current will flow, this I will also change. Okay, so we can decrease this resistance, therefore I will increase, therefore this potential will increase, which will also cause this potential to increase. Okay, if this potential is, call it E, then this potential is at this point, it is E multiplied by this this 54 divided by 110. So this is the potential at this point. So if we increase this current, this will increase, this will also increase. If we decrease this current, this will decrease, this will also decrease. So by this we can adjust the potential at this point, and therefore when this potential is same as 1.08 volt, we will get a null. Okay, and when we get a null, so after we get the null, this ensures that the voltage at 54 centimeter is equal to 1.08 volt. Okay, so once we do this, after that 54 centimeter is same as 1.08 volt. Okay, so okay, now yeah, so this side for ease of understanding assume to be 0 volt. Okay, then what do we have? If 54 centimeter is 1.08 volt, this ensures, so this implies 1 centimeter is equal to 1.08 volt divided by 54. Okay, 1.08 volt divided by 54. So this will be equal to 0.02 volt. Right, so 1 centimeter is now equivalent to 0.02 volt, and similarly any other value, say L centimeter, will be equal to 0.02 multiplied by L volt. Okay, so this step is called the calibration or standardization of the potentiometer. So this is this step 1. This is called the standardization or calibration of potentiometer. Okay, so now once this calibration is done, Then what we will do? We will disconnect this standard cell. So we will disconnect it here. Okay. And we will connect this galvanometer to this unknown source. Okay. So now the galvanometer is connected to the unknown source and this is open. So we can have a key, okay, with which we can switch between the standard and the unknown source. So now step 2, so this is the actual measurement step. The previous was the calibration or standardization. Now measurement. What we will do? Now we will not touch this R1 anymore. Okay. So we will not touch R1. We will not change R1 anymore. So which ensures the potential here is same as before, because the current is same as before. So that means now 1 centimeter of the wire is same as 0.02 volt and L centimeter is same as 0.02 into L volt. Okay. So this calibration is now same as whatever we have done in the previous step. So now we will not change the calibration, we will not change this R1. We will instead adjust the jockey. We will adjust the position of this jockey to find null. Now if we find, say for example, null at a position, say here, which is, say, this point, if this point is 90 centimeter, for example, okay. So if we find the null at 90 centimeter, then Ex, that is the unknown source, unknown value of this EMF, must be same as the potential drop from here to here within this 90 centimeter, which is equal to 90 centimeter multiplied by 0.2 volt per centimeter. Okay, because here we have this relationship, 1 centimeter is equivalent to 0.2 volt. So 90 centimeter is this. So this will come out to be 1.8 volt. Okay. So the unknown source Ex will come out to be 1.8 volt. Now some important points to observe are okay. So notes. So note 1, in the calibration phase, in the first step or the standardization phase, when we got the null with the standard cell at some length, which is 54 centimeter, that is what we have chosen. So at the null condition, no current was flowing through this cell. Yes. So there was no drop due to the internal resistance or the connecting wires, because no current was flowing. Okay. So this is important point. In the calibration phase, when null is obtained with the standard cell, no current was flowing through the cell, so there was no voltage drop. due to internal resistance. Okay, so unlike the previous scheme, if we had used the standard cell here, then the standard cell is delivering some current always, so there is always some voltage drop. But in this practical scheme, so when we got the null, at that point no current was flowing through this cell, so there was no voltage drop. Okay, let me call this E standard. Okay, so there was no voltage drop, so this potential 1.08 is a perfect value, is a correct value, there was no drop. Now next thing, also during the measurement of this unknown Ex, okay, so at the null condition there is no current which is flowing through Ex, so there will be no voltage drop in the Ex, and the EMF that we will measure is the correct EMF. Okay, so which was actually true in this circuit also. Even in this circuit there was no voltage drop during the measurement because there was no current at the null condition. So that is the beauty of potentiometer. Okay, so this is more important, that when, so in the measurement phase, at null condition no current flows through Ex, so there is no voltage drop, and we will get correct EMF. But if we had used a voltmeter to measure Ex like this, so this is the unknown Ex, if we connect this Ex to a voltmeter, and Ex has some internal resistance Ri, then all voltmeters practically draw some current. No matter how high is the internal resistance, this is not infinite. So practically we always have some small current. Okay, so therefore we will always have some small drop. And the measured value by this voltmeter will therefore be less than Ex. It will be Ex minus this drop. Okay, so if we had used a voltmeter to measure Ex, then the measured value will be less than the true EMF or open circuit EMF. Okay, so this is the beauty of, or the main property of a potentiometer, why one should use potentiometer. Okay, so if you recall, in our previous class we have mentioned that you can think that potentiometers are like ideal voltmeters whose internal resistance is infinite, so it draws no current and no voltage drop occurs due to internal resistance. Okay, but then, okay, you may ask, why do we not then use potentiometer always instead of using voltmeter? The practical reason is that to measure a voltage with potentiometer you have to adjust the null, and then only you will get the reading. But voltmeters give you live reading. Even if the voltage in unknown voltage is changing, you will have a live reading indicated by the pointer. With a potentiometer you cannot get live online reading always, so that's not easy to use. Okay, now Okay, so this point 1 is important because because the unknown because the standard cell doesn't suffer any voltage drop due to internal resistance, because at the null condition no current flows. And okay, and in another small important fact is that, so I have chosen this 54 centimeter, okay, to set the null. Why 54 centimeter? Why did I not choose 58 or 50 or 59 or anything else? Okay, so this choice was a bit of cleverness or a bit of common sense that I have applied, because I knew that I have the unknown source which is around 2 volt. That means, so when I will measure this 2 volt source, I would like this potential, this wire to have more than 2 volt. Okay, so only if this potentiometer has more than 2 volt, then only we can get a null. So I decided that, okay, let's have 2 volt at 100 centimeter. Okay, so I actually mentally calculated that. So let's set 2 volt at around 100 centimeter. Okay, and so then it implies this 1.08 volt, it will be at, so 100 divided by 2 into 1.08 centimeter, which is same as 50 into 1.08 centimeter. So that's what I did here. Okay, so I did this calculation mentally because I knew what I am going to do. So I wanted this point to be around 100 centimeter, also because then this value, that volt per centimeter, okay, so this volt per centimeter, this comes out to be a nice number like 0.02. It is not a fraction like 0.0257, 0.193. It's not a random fraction, it's a nice fraction, easy to calculate. So that's how I did it. Okay, so in the lab also, if you do an experiment with the potentiometer, you have to intelligently, cleverly set your calibration length like this, with the knowledge of the unknown source, how the value of unknown source, is it around 2 volt, is it around 5 volt, accordingly you have to do the choice. Okay, and okay, so therefore one more thing, okay, one more small thing is that now we will need this U1 to be greater than, definitely greater than 2 volt. Maybe we will choose this somewhat around 4 volt. Okay, so that, or maybe 3 volt, that is also okay. Otherwise we will never get more than 2 volt here. If we do not get more than 2 volt, then we cannot find the null, we cannot find the balance. Another last small practical fact is, okay, what we can do, what we should do is, we may put an ammeter here, or any meter, any galvanometer. Okay, this is an ammeter, it's an ammeter. Okay, this ammeter is to ensure that the current in this wire I is not changing. Okay, so this ammeter is to ensure that current I is not changing. Otherwise, what may happen? Say that in the calibration step, I set 1 centimeter equal to 0.02 volt by finding the null and by adjusting R1. But in the measurement step, when I come in the measurement step, by then say this battery discharges and this current drops. Then this 1 centimeter equal to 0.02 volt is no longer true. Therefore, the measurement will be wrong. So, we need an ammeter, so that we look at the reading of this ammeter after the calibration, and then once again we check that reading after the measurement, and if we see the current is changing, okay, then there is something wrong. We have to do the experiment again. Maybe we have to change this battery. But if we see this current is not changing, then our experiment is fine. So, this ammeter is to ensure that this current is not changing, but this is not to measure this current. Okay? I mean, not we will never read the value of this current and then multiply the resistance with this current to get the voltage here. No, that is not the way to, that is not why we have this ammeter, because this is mainly to ensure that this current is not changing. Okay? Okay. So, thank you. In our next class, we will talk about AC potentiometers. So, by then when you come back, please make sure you understand the necessity of these two steps, calibration, that means standardization, and the measurement very well. Okay. And yeah, we will meet again in our next class. Thank you.